series of lectures with our first lecture now. So the whole series is, the title is sparse graphs. So of course, it's a very wide topic, so we chose some particular areas, some we are more familiar with also. So the idea is that today we will introduce treewidth, and we'll spend time today and tomorrow on treewidth, which we will come back bit by little also. And then we'll have planar graphs a little bit later in the week, and next week will be dedicated to bounded expansion. So this week is only treewidth and planar graphs. All right. So, okay, one thing is that, treewidth is a super classic topic, so many of you might already know about it, so I hope it will not be too boring for you. Yeah, so if you know the topic already, then you can already think of how you would teach it. So that's also a nice thing, because different people teach differently. I have to say, I'm taking Ignace Sissot, who is an expert in treewidth, and so I have seen his lectures, and I really like the way he teaches, so I got inspired by him to introduce treewidth. And especially, I think, for people who are not familiar with algorithms, but who know graphs well, it could be it's a good way to go in this style I will use, which will be to talk about partial state trees first, but we'll go to that a bit later. Let me first, try to give you a bit of motivation. Why do we want to care about sparse graphs? What does it mean to be sparse, actually? It's not a very well-defined thing. So what's one of the general goals when we study graph theory or graph algorithms? So the idea is to find structure, right? Because many problems we are looking at, so whether it is from the algorithmic side or from the structural side, in general graphs, sometimes you can say something, but the general graphs are too general, and many times we cannot solve the problem. So the general graphs, the general goal in combinatorics, let's say, is find structure in graphs. So maybe there are general graphs where you don't find any structure, it's completely strange. So what can we do to find structure and solve the problems which are interesting for us? Okay, so what would be the goal? So for example, solve combinatorial problem. So one prominent problem is, for example, coloring, right? So you know that on general graphs, you will have a huge number of colors, but we know, for example, on planar graphs that we can use just 4 colors, right? So solve combinatorial problems for special cases. This is one thing, and for those who are more interested in algorithms, also develop efficient algorithms. So imagine you have a problem like, let's say coloring again, which is NP-hard problems. Efficient algorithms for problems. So in general, you cannot solve it optimally in polynomial time, but maybe if you have a lot of structure, again, if you take planar graphs, you can actually solve for coloring at least, or very easily. In linear time you can find for coloring, quadratic time, I think. So these are the two goals, find structure. So what do we do? There are many ways to find structure. Maybe I will start with the ones we will not see today, or this week's. One possible thing is to look at geometric intersection graphs, for example. This has been very successful. Alright, so you take some geometric objects, let's say disks. Okay, so this is very natural in many applications. So you take disks in the plane and you say, like, I want a vertex for every disk, and I make them adjacent if they intersect. So this is an area called geometric intersection graph. You can find structure. But this is not exactly our topic, so we want to do different things. But other people have also looked at forbidding some structures. So one very successful branch in graph theory and graph algorithms is, for example, perfect graphs. You must have heard it, which is more generally forbidding an induced subgraph. So, for example, and there you can also have very nice techniques. So this is really perfect graphs. There is maybe other ones you can think of, but these are the ones I can think of from the top of my head, which have been very successful in graph theory and graph algorithms. And then also sparse graphs. So maybe some prominent examples of sparse graphs that you know are actually trees, planar graphs. So they're very famous for a long time. But what does it really mean to be sparse? So this is not very clear. This is also not very well defined. But maybe, so quite recently, there has been an attempt by Nechetril and also Menendez. So Yannick Nechetril, he's a prominent graph theorist from Prague. Also Menendez, he's a French graph theorist and long-time collaborator. And so they wrote a book. I mean, they first wrote a series of papers in the early 2000s, I would say, and then they made it a book, I think 2012, called Sparsity. And basically what they try to do is they try to unify many small results from the literature and try to define what does it mean to be a sparse graph. And again, I mean, it doesn't mean this is the only definition of sparse graph. Sparse graph can mean what you want it to mean, but what is nice with their book is that they have a very robust theory of what it means to be a sparse graph. And many equivalent definitions and so on and so on. But so we will scratch the surface of this topic. It's a very vast topic. Even their book is quite vast. We will scratch the surface next week when we'll go at the classes of bounded expansion. But this week we will look at more old or well understood classes of sparse graphs, which are graphs of bounded treewidth and diagrams. So here I wrote a little diagram. I mean, maybe you can't see from the back, but the idea is that I want this to stay. I really like this kind of diagrams. So this is a graph class inclusion diagram, where these graph classes are more general. So here you see very simple graphs like path forests, so just disjoint union of paths, normal forests, which is disjoint union of trees, autoplanar graphs, planar graphs. So the ones we are covering. Here you can see bounded treewidth. So this is one that we'll mainly cover at the beginning, then there will be planar graphs. And the bounded expansion, they're sitting here. So you see that they're generalized. Also these things. Oh, there are probably some links missing. This is not exhaustive, there are many more nice graph classes. But this is a nice diagram. And the book of Nechetril and also Menendez, I mean, these bounded expansion graphs, they play a very important role. And they actually define something more general, which they call nowhere dense graphs. So it's sitting here, which we will not cover, but maybe we'll just mention it next week. And then you also have related classes which are not sparse, so to speak, but like graphs of bounded click width, bounded twin width, VC dimension, etc. But they are kind of related. So this is kind of a global picture of what is happening. So this is our motivation. And yeah, in the book actually, and also, I mean, the book is already, I think, 12, 13 years old. Since then, there have been a huge development also of the field. And especially, I mean, what people are currently doing in the research is, so these things are now relatively well established. People are nowadays trying to lift these topics to dense graphs. So exactly these. You probably maybe heard of graphs of bounded twin width, and there are more newer notions which they try to generalize all these things to dense graphs. So, but anyway, we will. This is the current research activity, which I'm not too familiar with, but we will stay with these sparse graphs. All right. So, well, before we start more in detail, maybe I have to start with the boring stuff to just be sure that everybody is on the same page, just to give some notations and small definitions that we will use. I'll do that here. Is it okay in the back? Or is it with the microphone? Is it fine? All right. Well, I think everybody knows here. So graph is, you have two things. You have the graph G. You have a set V of G of vertices and E of G of edges. Okay, so usually we will try, I mean, we might deviate a little bit sometimes, but we try to denote the number of vertices as n, and the number of edges as m. Alright, so this is called the order. And this is sometimes called the size, but there's sometimes a confusion because sometimes people say size for the order, so I will not be too particular about that. So this is the number of vertices and the number of edges. Okay, so one important measure is the degree of a vertex. Degree of a vertex. So that's just the number of neighbors, so number of neighbors. Okay. And then you have special degrees, which you can, special things for, you can apply for the entire graph. So the minimum degree of the graph. Okay. Delta of G. So this is, I need to write it in, it's obvious. The smallest degree you can find in the graph. The maximum degree. Delta of G. Okay, and the average degree. Average degree. Maybe we can denote that this d bar. Okay, so the average degree is just, you just sum all the degrees of your vertices and you divide by the order n. Okay, so this is a uniform kind of measure to can see, and this, of course, is important to measure what is a sparse graph. This is one way to measure a sparse graph, that it has a small average degree. We'll come back to that a little bit later.
And you mean simple graphs?
Yeah, and I think we will do simple graphs. We will need other types. So we'll not do directed graphs, for sure. We'll not do infinite graphs. We'll do finite. Simple. I mean, maybe sometimes we will need multigraphs. I'm not sure in some of the proof, but this is not very important. Well, actually, it is important because if you allow many parallel edges, let's say in a planar graph, you can blow up the number of edges. So it is kind of important. So yes, we will really consider simple graphs. Okay. Well, we have a notion of the subgraph. So H. Subgraph of G, so that just means that its edge set and vertex set are subsets. So that means E of H is included in E of G, and E of H is included in E of G. And then we have the notion of induced subgraph. Subgraph. So we'll say it's induced by some subset edge subgraph. Induced by S, which is included in G, subgraph of G. And it basically means that you just, in some sense, you just take your graph G and you delete the vertices which are not in S. And what you get is the induced subgraph. You have E of H is S, and E of H is just all the possible edges. This is all the edges in the graph, such that both X, Y are S. So here you can't just delete edges, whereas for a normal subgraph you can delete edges as you like. You can only delete vertices. This is what it means. And so this brings us to, you can define graph classes using these two concepts, and there will be two graph classes, which will be types of graph classes. Monotone graph class. So what do I mean by graph class? I just mean a set of graphs. Monotone graph class. So what is a monotone graph class? This is a graph class that is stable by subgraphs. So you can delete edges, you can delete vertices, you're still in the class. Stable by taking subgraphs. Whereas, okay, so for example, if you take the class of trees, which is not monotone, because if you take, you remove an edge, what you get two trees, so you get forest. However, the class of forests, this is monotone because you can delete vertices and edges, you still get a forest. And then another standard type of graph class is hereditary graph class. So that means stable by taking inducer. This is not crucial, but still I want to point out that. So most of the things we will say, in fact, these 2 weeks will be about monotone graph classes. So it's, I mean, in some sense, you are imposing more restriction on your graph class when you take monotone graph class, because you want it. It's a stronger property that you should be stable by deleting things, even edges. Hereditary is a bit weaker because you only need that it's stable by taking inducer. So, in other words, deleting vertices. You're not allowed to just delete edges. So this is more important in the context of like perfect graphs and when you deal with induced subgraphs, forbidding induced subgraphs, for example. But in our context, it will be less, or we will not use that.
What does this mean, stable?
Sorry? Stable means you stay in the class. So that means if you take subgraphs, you stay in your class.
Closed. Closed under subgraph.
Closed, yes. Yeah, you can say it. Closed under. Okay, so for example, let's say forest. Forest or planar graphs, you can delete things, you still stay forest if you're a forest, or if you're a planar graph, you still become planar, stay planar because your drawing doesn't change.
But trees are not, for example.
Yeah, trees are not, and they're neither monotone nor hereditary.
Yeah.
Yes.
So any example which passes the first stage, one down the second?
Yes. Because if you are monotone, yes, you are. If you're stable by taking subgraphs, you're also stable by induced subgraphs. But the reverse, for example, typically if you want to induce a graph as a, sorry, you want to forbid a graph as an induced subgraph. Okay, maybe, I don't know, you want to forbid P4 as an induced subgraph. Okay, so for example, I have this graph. This is certainly in my class, so no P4 as induced subgraph. This is fine because it has P4 but not induced. Okay. But now it is not monotone, this class, because this graph is in the class. And then if I delete this, if it were monotone, this should stay, but now I get a P4. So the graph class of which forbids P4s as induced subgraphs is hereditary but not monotone. And why it is hereditary? Well, because if you are forbidding a P4, if you keep deleting vertices, you're not going to create a P4. So you really need, if you didn't have a P4 in the first place, you would really need to delete some edge at some point to get a P4 induced.
One easy example will be set of complete graphs.
Complete graphs.
You take induced subgraph, they are complete graphs. But
Yes.
subgraphs you can delete edges.
Yes, correct. Yes. If you take all the complete graphs, all the subgraphs of complete graphs, this is just all graphs actually. You can create any graph as a subgraph of a complete graph. Not induced. Alright. Okay, and maybe just one last bit is about these asymptotic notations, because I might at some point write big O and little o and things like that. Most of you know that, but I have to repeat just in case. So when we have some functions, or should I use this one? Well, we'll consider just functions of the integers. This will be enough for our purposes, since we are doing discrete mathematics. Yeah, so this is well known for combinatorialists and algorithmics people. So we say that f is a big O of G. So sometimes people write equal, I prefer belongs to, but it's really the same. It's notation, so if you want, so you should have some index and 0 and n, and you should have some constant, let's say r, such that for every n greater or equal than 0, your f of n is at most c times g of n. Okay, so this is essentially this is a classic notation, asymptotic notation, which tells you that your first function is not too much bigger, or bounded constant away from your other function g. Okay, so the classic diagram that you draw is that, so because at the beginning we don't care about anything, this is our n0, this is like this, things can be crazy, but so what is this? This is c times g of n, and this is f of n. So after some point my f should be smaller than the constant times g.
So you want a positive series?
Yeah, positive. I don't know how you write that in India, but okay. Alright. Then you have the symmetric definition, which is big omega, which is essentially the reverse. You're taking the same definition, but you want at least. So this is a upper bound. This is the same as a lower bound. So you want f of n to be at least some constant times g of n. So the constant could be also less than 1. We play with that. But the constant can be just a decreasing factor. Okay, and then we usually write theta when both happen. And the theta just means that, yeah, you're really, up to constants, you're kind of the same asymptotically than the other function. This is the more precise thing, so this means it's big O, G, and it's big omega, G. Okay, so it means, yeah, you're kind of sandwiched between your one constant and your g. The constant will not be the same. One constant and your g, and another constant times your g. Well, essentially you're saying up to constants. And then maybe we'll need of g. So little o means that your order of magnitude is smaller, so it means that the limit f by g and right. So this f function should be dwarfed by this g function when n is large. And we may write, I don't think we'll use that, but anyway. first fraction is little omega. But I think we're not used. Okay. So these are just classic notations which, yeah, in algorithms and in combinatorics we are just, often we are just interested on the asymptotics, when things get large. So that's why we use these convenient notations. Okay, let's start with more interesting stuff. But before still going into the main things I want to tell, maybe still I will continue my line of things about the motivation. So I told you that we're interested in finding structure in graphs, both with the keeping in mind the goal of finding good combinatorial results and algorithmic results, which we don't have in general graphs. So I said sparse graphs. So I said, yeah, these guys have a good book on what is a sparse graph. But okay, what is a dense graph? Maybe we should first. So dense is the opposite of sparse, of course. What is a dense graph? So these are the things we don't want to study, or we want to forbid. So of course, complete graphs. They are the densest possible, right? Complete graphs that have complete graph Kn, and choose 2 edges. So that's the most you can do when you do simple graphs. Of course, otherwise you can get any number. So this is definitely dense. So generally what we usually call dense, most people call dense, is a graph which has roughly n squared edges. If we have n squared edges, okay, so of course you see I'm using asymptotic notation. It doesn't really make too much sense if you have a fixed graph. So this is a little bit abusive, but of course if you take the set of complete graphs, this is an infinite family, right? So you can use asymptotic notations. So when I will talk about graphs, I will usually implicitly mean, if I ask for dense graphs, I will, mean that we are considering some infinite family of graphs, and we want to say that they're dense, like I'm doing for the complete graphs. So if your family has members which have order n squared edges, we call them dense. Okay, so typical examples, maybe a complete bipartite graph, right? This has, if you take both sides to be the same, n by 2, you'll get n½ squared, so n squared by 4, so this is definitely dense. Okay, maybe if you like random graphs, you take a random graph, Erdős-Kényi random graph with probability p, where p is a constant. P is a constant. This gives you a very dense graph, because every edge will appear with a constant probability. So essentially, you will take all the possible edges, which is n choose 2, times this probability. This will be your expected number of edges. Random graph. Of course, this probability should be a constant. Let's say 1/2. This is the most typical example. Okay. Okay, and generally, we could say that if your graphs have linear, well, if you have another example, linear minimum degree. So that means every vertex is connected to some constant fraction of the other vertices. So of course this will be a dense graph, because in total you have n vertices, so there will be roughly n squared edge times a constant in minimum degree. Yeah, and so in general, this means what? This means linear average degree. So of course, if I talk about all the edges, if I divide by n, so if I speak about all the edges, I can just speak about one vertex, and it will have linear average degree. So these are the same things, right? Having n squared, roughly n squared edges and a linear average degree. It's just another view. So this is what we mean by dense graphs. Okay, so what are sparse graphs? Maybe sparse graph you can say, those which are not dense. This one maybe not be complete. Okay, well, I mean, you could repeat just these examples and tweak them a little bit on dense graphs. So, of course, you could take something which, I mean, if you want to be completely tautological, you can say set linear average degree, little of n. So what it may be log n or square root n. If you have square root n average degree, you will have roughly n square root n edges. If you have a log n average degree, you will have roughly n log n number of edges, and so on. So, for example, a good example are hypercubes. Hypercube on n 2 to the d vertices. Right, so this has roughly look at edges. In general, if you take a regular graph, but your degree is something which is, let's say, log n or square root n, of course you will have also, but let's say d-regular graph. If d is little of n, like log n, for example, let's just generalize this. Okay, you could also take a random graph, but now you, instead of a constant, you take something which tends to 0. Some function which tends to 0, and that will also give you an example. Anyway, you can find many examples. But this is not exactly what most people call sparse. So these certainly dynamic, it's difficult to call them dense, because they don't have a quadratic number of edges, but is it really sparse? At least traditionally, I think, in most contexts, people, what they really call sparse is actually when the number of edges is linear. Sparse, linear number of edges. Linear or very close to linear. In fact, I mean, in the book of Nichetrilenos and Mendes, they might allow some n log n will be still sparse on them. This is another interpretation. At least the graphs we will consider in these 2 weeks, we will actually, they will all have linear number of edges. So if you look at treewidth linear graphs, classes of bounded expansion, they contain only linearly many number of edges. Okay, so examples are forests, again, linear graphs. Right, we know that forests have at most n-1 edges. Planar graphs you will see later in the week how to bound the number of edges. It's roughly 3n, things like that. Maybe, you know, degenerate graphs. Degenerate graphs. So what is degenerate? Maybe I can. This I think will come. Maybe again and again. So what is a degenerate graph? D is a constant. Well, it doesn't have to be constant, it's a number. Degenerate means that you can so your complete graph on T vertices is degenerate. Well, let's not do it like this. Let's start with a single vertex K1. Degenerate, and if G is degenerate, if you add a vertex of degree at most D, vertex at most D, you are still degenerate. It's kind of an inductive definition. So you can build your graph by a sequence of adding vertices, but each time you add, the new number of edges you're adding is at most D. So this is called degenerate. So the new added vertices, they might not stay of degree D, at most D, but at least at the time you insert them, they have degree at most d.
So this subgraph will have maximum degree, minimum degree g, d.
Yes, at most. Yes. So, or in other words, you can, once you have built your graph and you're finished adding these vertices, you can peel off backwards the graph by removing vertices of degree d. So this shows you that you have at most d times dn number of edges. This is called degenerate. Of course, this includes, this is more general than graphs of degree at most d, right? If delta of g is at most d, this is also degenerate, obviously. Because everybody has degree at most d, even in the last, in the final class. Yeah, so this actually I should have started among, at first I think this is a very classic class of, when d is a constant, this is a very classic class of sparse graphs, right? Because you have at most delta n by 2 edges. So these are very, like, considered, let's say, subcubic graphs. It's a very interesting and nice and fast, but they don't have any edges. Actually, they have at most 3n by 2 edges. Okay, so these are considered, yes?
How do you check that the new G is in that class?
So you take a graph in the class, and you add a new vertex, you make it adjacent to at most d old vertices. It's a construction, right? So I'm not talking about checking, that is a different thing, but I'm saying you can build them like that. But if you want to check, sorry?
If there are total less than b vertices, then it will always be.
Yes, of course. Yes.
Degenerate is the upper bound of the maximum degree?
Sorry?
In a degenerate graph, is the upper bound of the maximum degree?
No, if you have a maximum degree delta, then you are degenerate. Right. Sorry. So this implies. I mean, I should have started with that actually. I forgot. So this is a simpler class, maximum degree d, and you can generalize that to degenerate. So this is an important graph class. So to check if something is degenerate, you could just look for a vertex of degree at most d, remove it, remove all the vertices of degree at most d, and iteratively you do like that. If you can peel off your graph and you get down to like one vertex, then you're degenerate. You can also do an algorithm to check.
So degenerate graphs are monotone graphs?
Yes, because you're not going to increase any degree or something by removing stuff.
And plus, if G is suppose 5 degenerate, then it is also 4 degenerate, maybe.
Yes.
And
Yes.
yes.
No, 6.
At most. If it is 5 degenerate, it may not be 4 degenerate.
Oh, sorry. Yes.
But
Oh yeah, the reverse. Sorry. Yes, the reverse. I think that's what you meant. Okay. So these are typical classes of sparse graphs, which they have been studied for, of course. Like these have been studied for decades. Of edges, or if you want to, so to speak, it's the same as constant average. Right, that's what it means. Linear number of edges, constant average. But this is not satisfying. So I don't want to define sparse graphs like that, or at least Neshatil and Jimenez didn't like that. So consider this example, where you have a peak with square root n vertices, and then you attach a very long path of size of length n minus square root. Right, so you have n vertices, and you have a linear number of edges, because here you have square root n choose 2 edges, which is roughly n, and then the rest is just giving you some 2 times this, or 1 times this, right? So this has a constant average degree. But in some sense, it looks a bit dense, right? Because this is a large peak. We don't want that. So this is just to say that the average degree is not a good measure for, maybe not a good measure for being sparse. It's globally, yes, sure. But you can get this kind of extreme example, or even more extreme, you add isolated vertices if you like. You add a huge number of them. But you will have these big peaks, so this is not very nice. Another example that they give is, take a complete graph, Kn, as large as you want, And then what you do, you subdivide every edge. So this has, I choose 2 edges, and now I subdivide every edge, so that means I create a new vertex. Every edge. Now you see, this graph is actually too degenerate, because I can peel it off by taking out vertices of degree 2, and I just come to a set of isolated points, and then I can remove them. So this has actually at most 2 edges. So this is any complete graph, I subdivide every edge once. So it doesn't have so many edges, where n, well, sorry, this is not the, let's see, okay, and this is 2n, where n is what is 2 times, okay, choose 2, right? So n is the number of vertices of this new graph. So this is also not satisfying. So why the argument is here that, sure, we are sparse in general, but in some sense the big peak is hidden behind the structure of this graph. And so we also don't really like that. So this we don't want to count as sparse. But that we will, for this we will probably answer that more next week with the classes of bounded expansion, which they will not allow this kind of things. But yeah, this is kind of the underlying idea of the sparsity framework, that you want to define a nice robust notion of sparsity where you are uniformly sparse, you are everywhere sparse in some sense. In fact, well, their book is called Sparsity, and one of their main classes, I mean their most important classes, is nowhere dense graphs, which we will not cover in these lectures. You see that the word is nowhere dense. So they want a graph which is nowhere dense. We want it to be, or if you want to say, everywhere sparse. So
What was the construction? Last one?
So you take a complete graph of your choice, any number of vertices, and for every edge you create a new vertex which is sitting on that edge. And it has exactly 2 neighbors, which are equal. So it's called subdividing complete. So you subdivide each edge once. This is the technical term. All right. So of course I'm slower than I expected. It's always like that. But that's okay. Okay. Anyway, this is maybe the end of my introduction. So this is just to give you a motivation and how to think about sparse graphs and why people have come up with definitions we will see interplay between different graph classes. And now I will start to introduce one very prominent classes of graphs, which is the notion of treewidth and graph classes of bounded treewidth. Graphs of bounded treewidth. And okay, I think most applications, or why this has been a huge success story. I mean, this notion I think was popularized by Robertson and Seymour in their so they came up with this in the 80s. Robertson and Seymour. I mean, these are giants of graph theory, so they made this huge work which took them 20 years to write down about minors and so on. But one of the main tools they introduced and they studied was these bounded treewidth classes. So this is a very successful story. And then, so for example, there are things like people like Corsell who studied the algorithmic properties of these graphs. And they were able to show that for these graphs you can solve so many hard problems in efficient time, linear time. So these two are Americans, Corsell is French. But actually the story was that so he proved this theorem I think in the late 80s, but they were all racing to that theorem, so they kind of had the ideas, but he was the one who got it first. And in fact, it's interesting. I mean, I have a department of computer science, so we have many colleagues that they have nothing to do with graphs, they hate graphs. But many of them, they know graphs of bounded treewidth. Like, there's one colleague who does databases, there's one colleague who does linear optimization. And then they have structures which, when they take their structures, which have not, initially nothing to do with graph or data science or whatever, and then they create a graph out of it, and then they have nice algorithms when these databases or things have bounded tree width. So this is actually very useful even outside of graph algorithms. In many topics you will find that. But this is nice. So this is a very good motivation to study them. Robertson and Seymour initially, they didn't care too much about algorithms. They had more combinatorial and structural work, but they also studied algorithms a lot. And this gave rise also to the field of parameterized complexity, which has also been very prominent. Yeah. So these graphs are very, very important. So the idea will be that today and tomorrow we will try to get acquainted with them. But I will start with some more prehistoric notion, which actually was introduced in the 70s, so 60s, 70s, which is the notion of a K-tree. Okay, so this is, I think this dates back to, I'm not sure if Harari really worked with these, but there was a person called Rose, some Americans. So Frank Harari was a very famous guy from graph theory. He developed graph theory in the 60s and later. And Rose, I know, has papers on K-trees. Yeah, early 70s this happened. The idea was to generalize trees. Right? Trees are, well, studied from the beginning of graph theory. So what is a K-tree? So we'll give a recursive definition. So if you take K, so the complete graph on K vertices, it's a K-tree. So it will be a little bit like the degenerate graphs, the definition. So if G is a K-tree, you choose a clique, K-clique of G, and what do? You attach a new vertex to that K-clique. Let's give it a name C. Attach a new vertex to a vertex of C, and this is also a K-tree. So this results in K-tree. Okay. So this is
Flo?
yeah.
When you attach a new vertex, you attach it with k minus 1, so that totally becomes k. It depends on your convention.
Oh, one tree is a tree.
No, you're right. This is
Yeah. This is actually very easy to get confused.
This is correct.
So thanks for the remark. I mean, by the way, in general, I might sometimes make mistakes and be inaccurate, so don't hesitate to correct me.
K-trees are like maximum K-tree with graphs, but AK has K minus 1.
Yes, I'm not speaking about tree width at the moment. I'll come back to that later.
Should it start with KK plus 1 or KK?
KK, so okay, let's give some examples. In fact, the whole business was to generalize trees. So, in fact, one trees, what are one trees? So one trees is you start with K1. This is a one tree. Okay. And what you can do is you can choose a clique of size 1 in your K tree and you can attach a new vertex to it. Right? So this is a one tree. This is a one tree. I don't have to go sequentially, I may, but I can go back to initial vertices. I just choose any one tree and attach. Okay? So what am I doing here? I'm just building a tree. Okay? So any tree is a one tree. Any one tree is a tree. These are one trees. So in fact, this was the motivation of these people to define this, right? They want to generalize trees. Let's do an example, which is maybe the nicest examples are one trees and two trees. So it can really help us understand what's going on. So in the two tree, what I do is two tree. start with K2. Okay. And then to build new fruit trees, I take my K2 and I take a key size 2. One. And I attach a new vertex. So this is a 2 tree. And I can repeat that. So in fact, what I'm doing here, as you see, while I'm attaching the new vertices, I'm just kind of gluing triangles to each other. But in a special way, I always choose an edge which is like this, and I attach it. I can do several times the same. So this is a 2 tree. Okay. So in fact, now you can see that this kind of looks like a tree, but I've replaced, in some sense I've replaced vertices by triangles. So it's a tree of triangles, right? You can see that it grows like a tree, and you can see that I'm never going to attach back, because each time I create a new vertex, I can't create a long cycle like this. So it will more or less look like a tree of triangles. It's very informal what I'm saying, but I think this is a good point of view. Tree of triangles.
I have a question.
Yes.
So, the tree is not supposed to be cyclic, right? So, triangles, they are cyclic.
Yes, so we'll allow cycles. We allow even large cycles. As you can see, there's a huge cycle. So it's not about the cycles, it's about the global shape of that graph.
The shape.
Global shape looks like a tree. In fact, you could see, you're at a good place, because if you zoom out, and if you zoom out sufficiently, these things will look like an edge, so you will actually have it will look like a tree. Of course, it's very informal what I'm saying, but this is the global level. Just think of it as a tree of triangles.
If you exclude the edge, apart from that, this graph is too connected, right? Except the edge example.
Yes, I guess it's. Yes. But we'll allow lesser connectivities in the moment. First, I want to start with this. Okay, so it's just to fix what happens for 3 trees, and I will stop at 3 trees because already 3 trees is a bit messy. So 3 trees, now you start with a triangle. And you will attach a new vertex and you make it adjacent to the triangle. So you will get a K4. Well, and this K4 is a 3 tree. Now I have to choose a triangle and make a new vertex. So let's say I choose this triangle next. I'm attaching this. Then now it's good, I put colors.
It's not a vertex.
This triangle. Now I can.
But
L01 is not the vertex.
Okay, where's the vertex? Oh, okay. Alright, thank you. So let's say I take this triangle. And take this one, etc. So you see now what I'm doing, I'm drawing a tree of K4s, pixel size 4. So if I keep doing it, it will look like a tree. This is like attaching a leaf to your tree, and it grows. Okay, so this is 3 trees. Right? So you could, by the way, one nice remark is that these 2 trees, you can actually draw them in a planar way. Because each time you're touching something, since you're just gluing to an edge, you can draw the vertex very, very close to the edge, and you're keeping planarity. So 2 trees are actually planar. 3 trees, not quite, but you could try, and it gives rise to a nice observation. What you do is, when you glue to the triangle, you will add in the middle. And you keep doing that. So as your triangles, you don't take any triangle. If I do here I'm no longer planar because like this, I have some parsing, but I'll not do that. I'm only choosing the faces. The triangles I'm choosing are faces, and then I will get a planar. These are very beautiful graphs, so they're called, these are planar 3 trees. On Wikipedia, they call them Apollonian networks. I mean, this is just a side remark. Nice class of graphs. Just planar 3 trees.
So if we take triangles as one vertex and we add everything to what is, if there is a common vertex, then it is a triangle.
Yes, that is the
That is why they are calling it.
exactly. I mean, I don't know if that is why. I would rather say it's because one trees are built like this from K1 and then touching. But I mean, you can see. I don't know why they call it K trees. Yes. You are correct. Okay. Exactly. So let's say I'm at step 2 of my construction. I've created it. I'm going to do this now. Again, and I'll try to. This is a good remark. See what she's saying. So she's saying, you take an edge, you touch this. Now, informally, what I will do, I will say that okay. You have seen that I was doing a collection of triangles glued to each other. So I will call this a new vertex. Like green. Well, green is maybe not a good choice. Red. Square red vertex. This vertex will represent my triangle. Now, if I'm doing like this, I'm creating a new red vertex, and I'm kind of attaching this triangle to this triangle. So I'm kind of creating a dual structure in red here, which will represent how my tree has been built. My 2 tree has been built. So if I do this, I might do it multiple times. So here, okay, now you have to be a little bit careful. This edge belongs to several triangles, but I'm going to take the oldest one, the one I have created first. So I'm going to attach like this. So indeed, I think this is what you meant. You are seeing a tree structure in red here, appearing. See that this is a tree. The way to show that this is a tree is because everybody has just a unique ancestor. That's why I put the arcs, by the way. The arcs is just to denote, oh, this is my ancestor in the tree. So when everybody has just a unique ancestor, this is a tree.
So is it the same thing like drawing a dual of a triangle?
In this case, yes. But, well,
It's not
no, is it the same thing? It is not the same thing because,
I mean, for the clarity is
right, if you take this, right, in the planar graph, you get this, right? Which is not exactly what I want. I want to attach these ones to this one.
No, common edge.
Yes. I mean, they have common edges, but it's not exactly the same. It's not the rule of the plane. But it is very much
Those
similar.
triangles are hanging on those that edge.
Yes. So it's a form of dual, but it's not the classic rule of the plane. It's not exactly. That's a good remark. And of course, when you have a K tree, which is not 2 tree, it's not planar at all. So of course, I could do that in the same way if I had a K tree.
No, K trees are not planar when K greater than equal to 4.
No, even for 3, they are not.
Three also.
Even for 3, they might not. So I drew some of them which are planar. They're beautiful, but it's not the generality.
So this is a 2 tree, right, which you have drawn,
This is a 2 tree.
and this is planar.
This is planar. 2 trees are always planar. Yes, but not 3 trees, not bigger ones. So let's give numbers to the vertices. Names to these vertices, right? So in fact, now what did I do? I drew a pink tree, and what I did, I associated every pink vertex with a triangle. So triangle is nothing else than 3 vertices. 3 3, 4, 5. So I'm just giving a label to these pink vertices. 7, 8, 9, which is this 3, 5, 6, 7. Okay. And in fact, here you see the underlying idea of, after the break, we'll see tree decompositions. So the tree decomposition will be this pink tree, essentially. And we'll associate to every node of my pink tree, we'll associate what we call a bag, which is a set of vertices. So in this case, these are the triangles. So the two essential properties of the tree decompositions will be that, first of all, every edge of your graph belongs to one of the bags, which is clearly the case here. My bags are the triangles. Everybody is in a triangle. So everybody will be in a bag somewhere. And moreover, the fundamental property of tree width, which is also here in this structure, is connectivity. If you look, let's look at vertex 3. Let's look at the vertex number 3, and let's look at which bags contain it. You see this bag, this bag, this bag, and this bag. And what you observe is that these purple vertices, they induce a connected subtree of our pink tree. And this is actually the case every time, for every vertex. If you take 7, 7 will be 7, 7 like this, these 4, and it is connected. And the reason why is this true, I mean, it's because how do we do these K-trees? I mean, we always glue an edge, so if you create a new triangle and one of the vertices is still there, that means you've kind of, pivoted around that like this, for example, or you've done this kind of thing, so you always have a connection to this. And when you have a connection to this, remember we are creating links like this, so you keep connectivity in the picture.
So number of new vertices is degree minus 1.
Sorry?
Number of new vertices. Number of new vertices in this decomposition under 3, it is degree of 3 minus 1.
Oh, you mean the bags?
Bags, right.
Bags, no, they have size 3. They are the triangles.
What I observe?
3. Oh, I don't get you.
Number of faces.
Number of faces.
Bases. Oh, maybe, I don't know. What? Well, I mean, no, you add a vertex, you create one face. No? Every vertex creates a new face. Anyway.
Right, not.
Okay. So this will be the underlying. So when we will go to tree width after the break, basically we will keep these properties, but we'll generalize. But this is where they come from. So just before we stop, I'll just. What's a partial K-tree? Well, it's very trivial. It's just a subgraph of a K-tree. Okay. So you do your K-tree. For example, you take your 2 tree. And you delete anything you like. You may delete edges. You may delete vertices. Of course, when you delete the vertex, you delete all the edges around it. Like that. Okay, so this is a partial 2 tree. Take the 2 tree, the K tree, and you delete anything like partial K tree. And now, what is interesting is now you're giving me. So these K trees they were very constrained, right? You had all these peaks. Now you give me any graph, and of course it's a partial K tree for some K. Why? Because if your graph has n vertices, you could have taken it as an n tree and deleted anything you like. So you are a partial n tree. So now the next thing would be to try to find the smallest K for which your graph is a K tree, a partial K tree. Why? Because the idea would be that even though you have deleted these edges, you can kind of remember them in some way. Like if you know that your graph is close to, could look like a 2 tree. You could use the tree structure of the K tree to do whatever you want to do with your graph. So this is a nice thing. Try to find the smallest K for which you are a partial K tree. Nice. Right, just so forests are partial 1 trees. You can see on this picture, cycles are partial 2 trees because I can take this as my 2 tree and then I delete everything which is inside and I get a cycle.
That is the max click size, na? Which is very difficult.
Size, I don't know. I'm not sure because you could. No, I don't think so. You could take a bipartite graph, complete bipartite graph. It has clique sizes 2, but you cannot do it as a 2 tree, for example, or 3 tree, or even any small K tree you can.
No, you were saying about partial K tree, no?
Yes. I mean, you still have to find this hidden structure, right? So here I give you the graph. It might have no cliques at all, I mean only 2 cliques.
No, a bipartite graph can be drawn as a partial 2 tree.
Complete bipartite graph? No, I don't think so. But
K33.
yes. But maybe you think about it during the break. I think that's a good time to do a small break, like just a couple of minutes. Cool off, and then I also need it. Thank you. I've seen this definition of K trees and partial K trees. Partial K trees, you're just allowed to remove anything you like. Right, so this is, yeah, so as you can, well, I had a good remark before, but when you look at K trees, I was speaking of monotone and hereditary classes. I mean, K trees are neither. Because if you delete vertices from a K tree, you might disconnect it completely, and K tree is always connected. So it is not a hereditary class, and it's also not monotone for the same reason. But partial K trees, however, are monotone. You take a K tree and you, I mean by definition, right? Because you're allowed to take subgraphs. So this is really the definition of being monotone. So the class of partial K trees is a monotone class. Okay. Right. So okay, maybe this tree here was not 100% clear, but it's not too important. But I hope the intuition is right there that yes, we're always creating a new vertex, and we will attach it to a unique father. Definition of that is the 100% clear, but anyway, what you get is this pink tree, and two main properties I highlighted was this. Every edge is containing a bag, and this connectivity property. And this is exactly how tree width has been defined, or rather to say tree decompositions. So we will now introduce this of the graph G. So you need a tree for that. That's why it's called a tree T. Okay? And exactly like here, so here this pink, T is this pink tree. And exactly like here, what we'll do is we will associate to every node of your tree. So I'll try to say node for the tree of the tree decomposition and vertex for the vertex of the graph. To try to not confuse the two. It's a bit confusing, but hopefully I will be consistent. So we have a tree T, and we have something with a family of bags. And family X, B, such that B is a node of my tree. Okay, maybe I'll use this notation, xi. So I'll use indexes I and j for the nodes of my tree. I've seen that in many papers. And so that V I can use for the vertices in my graph, again, to avoid confusion. So family xi, such that, sorry, I is a vertex. So for every vertex of your node of your tree, you are giving a bag. What is a bag? Bag is just a set of vertices of your graph G. Well, I should have written here. Sorry. So to every node of your tree, exactly like here, you associate a set of vertices of your graph G. So you want to, and somehow you want to embed your graph G inside a tree T. You don't do that just, I mean, of course you could do this completely arbitrarily. I take any tree, I put all the vertices, sure, or some random way, I don't want that. Such that the properties that I gave you here, I want to keep them also. Tree T, family bags, so they're called bags. So there are three properties, or in fact two of them. I told about two of them because one of them is kind of not that important in my opinion. So the first property is that for every edge x, y in my graph, okay, there should be at least one bag. There exists some node of my tree such that both x and y are included in my bag. So for every edge of your original graph G, you should find a bag which contains that edge, both endpoints of it. This is the first property. And this was kind of trivially true here because every edge will be in some triangle. And since the bags are all these new triangles I'm adding, so of course every edge is in some bag. And the second property, the third, this is actually the second. Well, maybe I can talk about the first. What is the first? I mean, the first is just tells that every vertex should be in a bag, which is almost always implied by the second. But for consistency, it has to be there because essentially, if you have an isolated vertex, the second wouldn't imply the first. But it is really not important. It's just to deal with isolated vertex. So over every x, same thing. There exists tree T such that x belongs to x. This is to deal with isolated vertices. So an isolated vertex is a vertex of degree 0 with no neighbor. So if I don't have these guys, everybody is in an edge. Of course, since every edge is in a bag, every vertex is also in a bag. So this condition is just a technicality. The two important conditions are two, the one that every edge is in a bag, and the connectivity. So if you take a vertex of your graph G, so remember what I was saying here. I was saying if you take the bags containing a given vertex, here it is in purple for vertex 3, it forms a connected subtree. So this is exactly what I want to write. For every vertex of my graph, the set of nodes of T whose bag contains X forms a connected subtree. Okay?
Composition is unique.
is always written like that with 1. I was always wondering. But this is a good point, and I didn't notice that maybe 3 implies 1. Yeah. Or you could just say non-empty connected circuit. We don't need 1. We have to rewrite all the books. Remove this condition 1. Yeah. Anyway, these are the 2 essential properties. And so really the main takeaway message of today for me, even if you don't care that much about treewidth, is that just look at this picture, see your graph as a partial, if you have a partial K-tree, this actually is a tree decomposition of your graph. But this definition of tree decomposition, well, by the way, so this is Robertson and Seymour, I think 1994. I think, well, something similar existed also even before, but they used this name, they defined it formally like that, and this is now the standard way to define and the standard name, tree decomposition. So as you see, the tree I was defining here fits to this definition, but this is much more flexible. This is much more general. Doesn't have, my tree can be very strange, it doesn't have to come from this partial K tree.
Decomposition is unique or not?
Sorry?
Decomposition is unique.
Absolutely not. Not at all. I will show you. You can play around with it, in fact. You can take a tree decomposition and change it in a weird way, and as you wish, it will still remain, not as you wish, but you just keep these properties. And it will remain in tree decomposition. So it is a very flexible definition. Alright, what's the tree width? So first of all, the width. Your tree decomposition T. So this is how I will denote the tree decomposition. It's a pair where T is a tree, and this is the family of bags. Is the maximum size of a bag. Minus 1. Okay. So why this minus 1? Well, look, remember the K trees. In the 2 trees, my bags were triangles, but I call them 2 trees. So it is the same issue here. So I want to be close to the partial K trees. So the width of the tree decomposition is the maximum size of the bag, minus 1. But this is a very technical point. Also, I think what they usually tell, the story what they tell is that they didn't want trees to have tree width 0. They wanted trees to have tree width 1. But anyway, so sorry, they didn't want trees to have tree width 2. They wanted trees to have tree width 1. It's rather like this. So that's why they put this minus 1. And well, it makes sense when you look at this partial K trees, because also there it's a K tree, but that's says KM. Anyway, this is not very important. And what's the tree width? So what you want, essentially, our goal when we do a tree decomposition or when we try to find a graph as a partial K tree is to minimize this K, minimize the size of bags. And the tree width is the smallest you can achieve. So the tree width of G, denoted tree width of G, is the smallest width among all tree decompositions. Okay. So that's what we call tree width. You try to find a tree where your bags will be small as possible, and that's your tree width. If you think about the partial K trees, it's, yeah, you try to find K tree with K as small as possible, and you take that pink tree, it will fit with this definition. Proof was a proof by picture I did before. So any partial K tree has treewidth at most K. So this is, I'm not giving a formal proof, but this is the picture I was showing with the pink tree. You take, so what do? You take your graph. It's a partial K tree, so you know there is a K tree for which is a supergraph of the graph. You draw that K tree. You take that bag, a sequence of bags with a pink tree, which I did before, and this is your tree decomposition of your graph G. Okay. So the bags, so now every edge of the graph is also an edge of the K tree. So the bags of the K tree are these. Of course, the K tree has maybe many more edges, but that's not important, because you just want that every edge of the graph is in one of the bags. So it's not an if and only if condition. It's not like every bag should be a clique, you know, every bag should have all the edges. It's not like that. You just want that every edge is in the bag. So the reverse is also true. So treewidth at most K, partial K trees, is exactly the same. So what's the point then? Partial K trees, I mean, at least if you come from graphs, if you know graphs being partial K trees have a nice structure, they're easy. So why do we bother about the treewidth business? So the first time I saw this definition, I was a master's student. In fact, Purcell was my professor, and I didn't understand anything. So these three conditions, I think, it's difficult to get into it. So if you don't understand them, it's normal. It takes some time to understand and digest these things. It's not intuitive at all. But I like the view from partial K trees. I find it more intuitive than this. And in fact, these two other things are the same thing. So why do we bother? Well,
K minus 1, right? K minus 1, right? First line.
why? No. Because you take the bag size minus 1. Partial K tree has cliques of size K plus 1. Right? Or
Trees are 2 trees.
trees are 1 trees.
Tree with 1 is 1 tree.
Tree with 1 is 1 trees and partial 1 trees. Sorry. Tree with 1. So there's this, but it is always confusing. It is always, you have this bag size and width, which is one difference. Something very simple. Let's take this 2 tree. Okay? 1, 2, 3, 4, 5, 6. So this gives me as let's say the natural tree position, which comes from the 2 trees. Take pink like before. Looks like that. Right, so my tree decomposition, I will show it as this. This is my tree T. And the bags, in fact what I will do, I will draw the bags as nodes. So 1, 2, 3. So I'll put the bag as the label of that node, just to be a bit more concise. 1, 2, 4. 3, 5. 3, 6. Okay. So this is the, let's say, natural tree decomposition I get from this to view this as a 2 tree. You see, bag size is 3. Oh, let's actually remove vertices to edges to make it a little bit bit more interesting. So this is a partial 2 tree. You can see that every edge of your graph is in one of these triangles, so it's in one of the bags. And now if you look at these connectivity things, the ones form this, the 2s form this, the 3s form this. So you have the connectivity properties also. But now what I can do is I can also do this. Okay, still a tree decomposition. I didn't lose any of the properties. So this is a tree decomposition. I can do this. Right. Still a tree decomposition. So this shows that this I can even put the empty set. Still a tree decomposition. So you can see that this tree decomposition definition is much more flexible. Of course, you get this natural one, which is very concise and nice. And this point of view can be very interesting for some times, for some problems. But this is particularly interesting for algorithms, because we can fiddle around with that tree decomposition, make it simpler. Simpler, I mean, we will not decrease the size of the bags, but maybe the structure of the tree will be simpler, and then we can do algorithms in a better way. So that's why this definition is useful. So it is much more flexible. So tree decomposition is far from unique. You can see it now. Right. You can do practically, you can duplicate everything, you can do it in any shape you like. Of course, we don't want it to be too big. It's not very good. Yeah. By the way, if you take the tree decomposition that comes from this picture, it will have roughly n number of nodes in your tree. Because each time you're adding a new vertex, you're creating a new node. This now has, of course, many nodes in my tree. So you don't want to blow up that, but it's okay. No, because, as I said, the bags might not be clicks. It could be, so you know that you will be a subgraph. If you make every bag a click, you will be a subgraph of that. But you cannot recover the initial graph. But you could say that, yeah. In fact, the maximal graphs of treewidth k are those where the bags are cliques. And in fact, it is the same as chordal graphs. So when every bag is a clique, this is equivalent to chordal graphs for those who know chordal graphs. This is also very interesting. So chordal graphs have some connection to this treewidth.
Flo, maybe you can say what is chordal graph. I see.
Okay. So a chordal graph is chordal. Chordal means no. So every cycle of length at least 4 has a chord. Okay. That's not particularly enlightening, but what it means is you have a cycle. What is a chord? This is a chord. But here I have a cycle of length 4, still it needs a chord. So this is a chord graph.
You don't have any induced cycle of length 4 or more.
Another way to say it exactly is that no long induced cycle. Induced cycle is the same as chordless cycle, no chord. I want every cycle to have a chord. And there are very nice characterizations of chordal graphs. And yeah, one of them is that you have a tree decomposition where all the bags are cliques.
So chordal is too free?
No, but K trees are chordal. Okay. The K trees actually are chordal, like every time I was putting a clique, right? I mean, I cannot create an induced cycle, but a K tree may not be a 2 tree. But yeah, 2 trees are chordal.
The click sizes may be different.
Yeah, click sizes will be bigger. But yeah.
In K3, all the click sizes are the same, maybe.
Yes. Yeah, click size is K.
Because of that.
Maximum click almost all says K, except if you are click. Something like that. Yes. But by the way, an interesting remark, like two trees, I told you they're planar, and they're also chordal. So it's a nice class. They're both chordal and planar, which is kind of two quite different properties. So it's very nice. Alright, let's convince you that so G is let's say you have a 3D composition of a graph. Okay. G composition of G. Then every clique of the graph. So this is all the classic properties of 3D composition. Every clique of G is contained in some line. When I say contain, I mean entirely contain as a subset. Okay. If you think about the K-trees, this was true because all these maximal cliques, in fact, were become bags, so of course they're contained in a bag. But now in these, now we have 3D composition, it's much more strange. It's not clear immediately why this would be true. So the proof, how much time do I have? Proof will be, so you take your clique C, we're going to do induction on so we order the vertices arbitrarily of that clique induction C, so we are just going to prove little by little that there is a bag containing all of them. So B1, B2 is clear by the second property of the 3D composition. Because it's an edge. We said that every edge is in some bag, right? So the two first vertices, so the inductive hypothesis is that B1 up to BA, BI are in a bag. This is my inductive hypothesis. I'm proving it for I at most 2. It's a base case. This is clear by the second property because every edge is in this. And now, in fact, this is an interesting viewpoint on how to, it's another point of view of this 3D composition. Okay, it's completely arbitrary. And by the third property, we know that, so this is my graph G, I have a clique C. In fact, let's make this here. This G. B3, etc. So what we know by the third property, we know that if you look at the bags which contain V1, it forms a connected subtree. So I will draw it. It's something like this. This is V1. This, or in some sense, this represents all the bags containing V1. Maybe I call this T1. And then I have T2, T2. It looks like this. So this is all the bags containing V2, orange. And we know they have to intersect. So these two things have to intersect because by the second property, every edge is contained in a bag, so that means these two trees must be somewhere together in one node of the 3D composition. And this picture I think is nice because it gives you another point of view of what's happening in the 3D composition. You can see actually a 3D composition as just a collection of subtrees, where every subtree represents one vertex of your graph. And if there is an edge in your graph, these subtrees have to meet somewhere. So this is also in some, I have used that in a paper where it is more convenient to look at a 3D composition in this way, because you're interested in the adjacencies like that. You can reason about the trees. It's completely equivalent.
So if they meet, it's not necessary they will have an edge to subtract.
Yes, it is not necessary, but so they might have an edge or they might not.
Yes.
But if they have an edge, they have to meet. This is
And if you make it even only if I think it becomes a caudal graph.
exactly. So yes, so this is another connection. So there is a famous theorem of Gabriel that says that the graph is caudal if and only if it is the intersection graph of subtrees of the tree. So again, the maximal ones where every edge is there when there is an intersection, these are caudal graphs. But that's not too important now. I want to prove this proposition. Okay, so this is
the subtree corresponding to Vi and corresponding to Vj, they all must intersect somewhere, right? Because
yes, because we have a clique, exactly. So because we have a clique, all my mod C subtrees pairwise have to intersect. So if I take the third one, well, it has to intersect, this one, but it also has to intersect the pink one. But of course, it has to be connected itself. And this is where proof is going to go. I mean, if it has to be connected, it is not possible that it intersects one on one end and the other. They have to meet, right? So what will happen is this. Okay. So this is a bit maybe informal, but essentially what happens is that if they all pairwise intersect, they actually have to intersect in the common point. So you see, I will find at least one, and maybe more. I will find some bags where they are all meeting together. And I can keep adding this. If I add a new tree, it has to intersect the 3, and you can see that they will all meet. This, by the way, is called the Helly property. Of subtrees of a tree. This is a very classic thing. That's so Helly property means if you have a collection of sets and they pairwise intersect, then they all have a common intersection. That means this collection has the Helly property. So these subtrees of trees have this property. So since I know they all pairwise intersect, so this is not very formal. I'm not giving the formal details. It's just proof by picture, let's say. But you can easily convince yourself that they will have to meet all in one bag. This one there. So this property. This is the picture which shows this property.
What is the induction hypothesis like? What is the base case?
The base case was 2 vertices. So I have a clique of any size. I want to show that the induction is the first I elements of the clique all intersect in one bag. All belong to one particular bag. For 1 or 2, it is clear because of the second property of the treaty conclusion, which said that any edge was present in the bag. Okay. In fact, this is true for all the edges of the clique. So we know for any 2 actually they belong to some common bag. Now we have to show that they are all together in one bag.
so where did you use induction hypothesis there?
Well, I didn't really use it. It was a bit informal, but yeah.
I was writing a proof where you don't need Bernoulli induction.
Yeah, I mean,
So it's like sort of every edge has to be covered. That property itself is sort of
yeah.
crucial for the proof.
Yes. Yeah. So that's how I was. So this tells you that any 2 edges have to be in one bag. Okay, but now we have to show that they're all in the same bag. I think the easy thing is to say that the induction is here to say that, okay, you have the I minus 1 and they're all in one bag. Now when you add a new one, let's say they are in some bags. So you take the I plus 1th one. You show that it has to be somewhere in that place where they want to say. Because if it doesn't, what happens if it doesn't? So let's say you're taking color. Yeah, I don't know how to formalize this argument. But yeah, essentially, if it cannot be disconnected, and you have to show that it goes through this kind of block. So I don't have a formal argument now, but this is actually a question of the tutorial. So we'll think about it by something. I mean, of course, if you assume the Helly property of subtrees over trees, it is immediate. So this is how I have seen it always. And the Helly property is probably proved by induction, I'm not sure. Subtrees over tree. So assuming this, we prove is immediate. So this is really what we can show. We have to show. Okay, we are already over time. I just want to state one other property. Well, again, here these pictures are quite interesting to understand what's going on. So this property is about separators. So this is an important notion. A separator, also sometimes called vertex cut set. S. So it's a set of vertices of a graph, which disconnects the graph when you move it. The separator is a subset of vertices. And this is also a very important thing, especially to deal with the algorithms on bounded tree width, is that they have, these bags are essentially separators. Such that, so when you take all the vertices, except, I mean, you remove that separator, so you take the graph induced, this is the notation shows subgraph induced by the set, it has at least two components. This is called a separator. Okay, so just as a picture, you have your S. When you remove S, you get some graph which has at least two components, maybe a little bit more. This is called a separator. Yes. Well, separator. Yes. If it's disconnected, I mean, even an empty set is a separator. Okay, and in tree width, these graphs of bounded trees which have small separators. If you look at the two tree here, you can see that if I remove one of these triangles, I disconnect my graph. And this is the intuition that almost all of these triangles are actually separators of your graph. So you have separators of two trees, you have separators of size 3. This is a separator, this is. And the ones which are not separated are these ones, of course. If I do remove this, I still have one connected component. So you have to be a bit careful. You don't take the leaf bands here, but most of these other ones, the central ones, they are separated. And even more formally, the lemma I wanted to say, which is also very classic, is that if you take, you have a 3D composition, G, this is a 3D composition of your graph G. You take an edge of your, so take some ij being an edge of the tree, such that, so the technical property we need is that xi minus xj is different from nt, and xj minus xi different from nt. So this is to avoid these bad cases where I am a bag pair, which is at the leaf. So what I'm doing here is I'm taking two adjacent nodes in my tree, ij. This corresponds to two bags, which should intersect because if they don't intersect, I mean, the graph is not connected. what I'm saying is that this intersection here is a separator. So XA
Set of the tree.
yeah.
Then do we have to mention xi minus xj?
Yeah.
Not necessarily.
I think we have to.
We have to because you remember I could duplicate as much as I want these bags. So if you take 2 times the same bag, it will be in that situation. So you really want that. In fact, you really want that yours. So this is xi intersection xj.
In fact, there's also xj is fine. But then if.
So if this is empty or this is empty, you see that you're not disconnected. If your graph looks like this, so let's say one bag is included in the other. This is, the big one is, this is my graph. This is xi, this thing, and this is xj. And xj might not, the intersection might not this. And this is, in some sense you can see this, yeah, this will be a leaf in your tree composition. But we have to be careful because these tree compositions are too flexible, that's why you have to write. You cannot just take a leaf. You cannot take which is not a leaf, it will not work. Right? Remember I was doing 1, 2, 3, I could do 1, 2, 3 at once. I take this leaf, sorry, it's my let's just take leaf. So this is xj, and you know that here you have which are not. So the difference between each line. We want to show is that there is no path from A to B. Well, there's no path, something which is on this side, which means that there is no edge. And if there was an edge between A and B, because of the second property of tree width, these two would be in the same bag. But they induce a connected subtree-dimensional decomposition, each other. So they have to meet somewhere, but they cannot